Hi guys. So, going into this week's notes, go ahead and start you off with the first two pages are going to be pretty nice. First two pages, 29 and 30, not bad at all. 31's a little bit tough. No, sorry, that's incorrect. That's not how I should say things. Don't worry, guys, this is going to be easy. It's all going to be fine. But Mr. Knock, you always say it's going to be easy. Yeah, but this time it'll really be easy. Proceed with it not being easy. Yeah, that's what's going to happen. So, please make sure you're checking in my office hours this week if you need help. We are going to do an activity on Wednesday from 1 to 2 to help you with page 31 specifically. So, if you are available from 1 to 2 and can get on Zoom with us, it's going to be a great time. It will be beneficial, I think. So, you should definitely come on over and do that with me so that we can work together on that. Okay, so let's go in then to today. So, like I said, we're starting off on page 29. I'm trying things a little bit different this week. Instead of putting it up in the actual, whatever, it might even look different to you. It's a different program for me. Okay, so today we're talking about plotting polar coordinates, and polar coordinates are just like uh, like circular coordinates. Like the unit circle is technically polar coordinates. It's the graphing of polar coordinates. Granted, we did it with rectangular coordinates when we did it, but it's kind of the idea. It's the early introduction of what polar coordinates would look like, which is going to lead us to what we're talking about today. So, up till now, everything we've graphed has been on what we call the rectangular coordinate system, meaning there's an x value and a y value. That x value helps us dictate where it's going to go on this horizontal axis, while the y value helps us dictate what's happening on this vertical axis. So the change from rectangular, and we call it rectangular because think about it, if you were to draw the x-axis and then to the y-axis, ultimately you're making a rectangle, right? The polar coordinate system is a circular system. So to graph a polar coordinate, what we're going to do is we're going to have a fixed point that we would call the pole or the origin. And it's called the origin also in rectangular. That would be the point 0, 0. So in a polar coordinate system, there's also that point 0, 0, and we refer to that as the pole as well as the origin. It's called both those names. We would draw that initial ray, or we'd call it the polar axis, and the polar axis would be like 0 degrees and 180 degrees. Those would be your polar axis. That's your x-axis in a rectangular system. In the polar system, that's our polar axis, that flat, horizontal, 0 and 180 degree points. And just to kind of show you a little bit more drawings on here, you can see that right here I have what I would call the origin, right? And again, we called that the pole in this system. We have the polar axis, which would be this flat ray that goes across the bottom. And then we have two things in there, and these are going to look super familiar to you. We have theta that we called the directed angle. We saw that when we did our vectors just before spring break. Direction angle, directed angle, same thing. We also have the directed distance, or in a vector we call it the magnitude. These are almost the same exact thing. If you understood vectors, a lot of this information is going to kind of tie into this, and it's going to look very familiar. The polar coordinate that we'd call, like here I called it P, is always going to be, instead of being an x or y, it's going to be a radius and theta. The radius dictates how far we go out on our polar axis, and theta dictates how many degrees we rotate that ray to create our polar coordinate. So just as a reminder, the radius is our distance, or radius was the other use for it, and theta, the directed angle, always moves in a counterclockwise fashion. I believe I have my two examples today. So my first example is we're going to plot the given polar coordinates. So let me jump over to my example 1. So let's plot each polar coordinate, and I had two examples to try in here, two practice problems for example 1. So plotting the polar coordinates given below. So I have 2 and pi over 3, and 3 and negative pi over 6. So I think the first part that's going to be a little bit tough with this. Now let's start by just creating a graph, right? So we're still going to create a Cartesian coordinate plane system like this. The difference being is that my graph is not graph paper. It's not like nice straight lines going up and down and making little squares. We're going to make circles on this. So what I'm going to do is I'm going to go 1, 1, 1, 1. And I'm going to, at each of the spots that there is a 1, I'm going to attempt to draw a circle. Hear the words attempt. that is as accurate as I think I'm going to get. Okay, I could then go and graph all my 2's. So I could put 2, 2, 2, 2. And you know what? Why I have the black pen out? Let's just go 3, 3, 3, 3. And I would create a series of those. And I create a series of circles that go through each of those. So I've done my 1 circle. Now let's do the 2 circle. That's decent-ish. Just, pretend that's rounded. And then our 3 circle. Obviously, this will be far easier to do on paper than it is for me to do on my little pad. So that's what the graph, or the coordinate, like the plane for graphing these points would look like. So if I go to graph this point, the first thing I'm going to do is, remember we said that this is the radius and this is the directed angle theta. So I'm going to come out in the radius out to 2. So I'm going to take here, I'm going to go out to the second circle. So this whole second circle is where this point's going to show up somewhere. And then I'm going to graph the point, or I'm going to move pi over 3 degrees. Well, we know pi over 3 is going to be like, it's right in that first quadrant, right? And it's 60 degrees. So I'm going to go over the second ring for 2 as the radius. And then I'm going to go up to 60 degrees and put a point right there. So that right there would be my polar coordinate 2 and pi over 3. And in the book they had drawn the little ray that goes through it too. But specifically the point is right here. So let's try that again for this next one. I'm going to shortcut this one a little bit. I'm going to go 1, 2, 3, 1, 2, 3, 1, 2, 3. 1, 2, 3. And we'll just draw the ring around the third one. Like, technically we could draw the ring around, like, the 1, the 2, and the 3, but let's save some hassle here because this is hard on a computer. I'm getting better. I mean, if you watch the first video and this video, we've definitely improved, but, progress still. Okay, so in this one, we're still going to go out to the third radius, so over to about here. And then we're going to, instead of going, well, this one says go negative pi over 6. So I'm going to move in the negative direction, which means the clockwise direction. We know pi over 6 represents 30 degrees, so I'm going to go negative 30 degrees. So probably about there. And then draw our ray that goes through it. But again, this is the point that we're looking at. This is specifically the point 3, negative pi over 6. That ray is just the ray that kind of cuts through it. And that would be your graphs right there. That would be how to graph and plot the polar coordinates. So, oh, that's not what I meant to do. Hold on. That's what I meant to do. Okay, so coming back into our notes then, for those of you who maybe want a little bit cleaner of a picture because, that thing's hard to do. You can see a little bit cleaner of a picture right there with my actual notes. Hopefully that makes a little bit of sense there. Clears up any of that. If you need to pause it and write it down, that's it. Okay, so we have example 2 now. Before we get into example 2, that we're going to talk about this. Remember in the unit circle that we knew that if you added or subtracted 2 pi to a point, right? If you add 2 pi to pi over 2, you would end up with 5 pi over 2. You could also subtract 2 pi from pi over 2 and you get negative 3 pi over 2. We know all 3 of those things represent 90 though, right? If you take your unit circle, let me make sure I'm going I don't know which ways. I don't know. I can't do it on the air like I normally would. Because I don't know which way is left and right. Right, here's my 90, right? That's pi over 2. Well, if you go 2 more pi over 2, you would end up at 90 again. Or if you subtract pi over 2, you'd end up at 90 as well. All 3 of those things represent 90, and that idea carries over to polar coordinates, is that we can repeat polar coordinates just by adding 2 pi to them. Similarly, we can also change the sign of the radius. So in the 2 examples I showed you up here, we had a positive radius, and then we graphed our polar coordinate, right? What if, though, I did a negative radius and then graphed the polar coordinate? Well, what's going to end up happening then is it changes the direction by 180 degrees on the direction angle. So we also can represent the same point by adding 1 pi or subtracting 1 pi from the direction angle, but changing the sign of the radius. And to make that make a little bit more sense, what I did is I wrote out the 2 formulas here. So the radius theta, that polar coordinate, is equal to the radius and theta plus or minus 2 pi. and you can keep adding or subtracting 2 pi from it over and over n times. We also know that the radius theta, that polar coordinate, is also equal to negative radius and then adding pi or subtracting pi from theta. So you can switch the signs once on the radius and then only add pi one time or subtract pi one time. So let's look at an example of that. I think I only had one example for that one. So it says find two more representations of the point, the polar coordinate, -1 and 3 pi over 4. So the first thing that I did here is I graphed this. I wanted to see what it looked like to help me out a little bit in visualizing what's going on. So we're only working with 1. Makes this graph a little bit easier. I only have to draw one circle. Let's see if I can do this. Let's try this. Oh, but it's not a different color. Hold on. That's going to be so much prettier, though. Why didn't I do that before? What was I thinking? Oh, that's right. I wasn't thinking. Boom. Look at that. It's like I'm a professional. Okay, so I'm going to go to -1. So this time, instead of starting over here on the right side like we would normally start on a graphing, right? We're going to start over here on the left side. And again, I'm going to go 3 pi over 4, so we know that we're going to move in the counterclockwise direction. That's going to be this direction. So this is 1 pi over 4, 2 pi over 4, 3 pi over 4. So I know it's going to be right there. So right off the bat, I spot one representation of this that's really easy to do, and that's just doing the positive direction, right? You can see that in the standard setup that we learned in example 1, we went +1 and then they moved in the negative direction. So they went at a radius of +1, and then we moved this direction. Well, since it's 3 pi over 4 from here, we know it's only 1 pi over 4 away from here. So we know that to get there, we'd have to move in the negative direction, pi over 4 units, and that represents the same thing. So it's kind of like the standard version of it. Essentially, though, what I did there, right, I changed this sign to positive. So when this switches to positive, then it means that we have to add or subtract pi to this. So we took this number and we subtracted 1 pi away from it. So 3 pi over 4 minus an entire pi. Well, to make this be the same, we're going to have to multiply by the top and bottom to make the denominator the same. So I multiplied by 4 on top and bottom. So what that means is this becomes 4 pi over 4. And 3 pi over 4 minus 4 pi over 4 gives me negative pi. And then the 4 stays, so I get negative pi over 4. That's essentially what just happened there. But you can see, if you understood what we did in example 1, it's the same thing, right? Let me get rid of those arrows. There. Okay, so to get a second representation, this one we could think about the 2 pi version, right? This was the change the sign and add 1 pi or subtract 1 pi. The other one was to keep the sign the same, but take this and either add or subtract 2 pi. So I could take 3 pi over 4 and I could add 2 pi to it. So just like we did in that last one, we're going to have to multiply the top and the bottom by the number to make the denominator the same. So ultimately what that's going to cause this to become right here is 2 pi times 4 is 8 pi over 4. So I could add 3 pi over 4 to 8 pi over 4, and I would end up getting -1, and then 3 plus 8 is 11 pi over 4, and that would be the same thing. Again, there's a lot of varieties of this, though. I could also have subtracted 2 pi, and if I did that, I would have ended up with -5 pi over 4, and that's the same thing. I could have added another 2 pi to it, and I could have gotten 19 pi over 4, and that would be the same thing. So all those varieties work. It's just that if you switch the sign, you can add or subtract 1 pi to it. If you leave the sign the same, you can add or subtract 2 pi from that value and get it. So again, going back over to my notes so you can see my more clear, clean version of it. Getting there. There you go. This is what I had. I'm not sure what this cutoff. Oh, that's an 11. It doesn't look like a very good 11. I don't know why I had a moment with it. It does look like an 11 now that I'm saying it out loud, but it didn't look like an 11. So you can see the first rendition was that I changed the sign and subtracted 1 pi from it. And you can see the second rendition, I kept the sign the same and added 2 pi to it to get 11 pi over 4. So both those work. So let me know if you have any questions on that. Yeah, that's it. Page 29. Bye, y'all.